The sound entering your ear is simply a pressure wave, a vibration traveling through the air. Its defining characteristic is frequency, measured in hertz. Humans can theoretically perceive a range from 20 to 20,000 hertz, but this window isn't static. From the moment you are born, you begin to lose the ability to hear the highest frequencies, a process called presbycusis. It's a slow, inevitable decay of the tiny hair cells in your cochlea, the ones tuned to the highest pitches. This gradual loss is why a mosquito alarm, emitting a high-pitched whine around 17.4 kilohertz, is audible to teenagers but often silent to adults. The famous audio clip is built on this very principle. The acoustic information for the word Yanny is carried predominantly in higher frequency bands. The information for Laurel resides in the lower ones. Your age, your listening history, even the quality of the speakers you use pre-selects which set of data your brain receives more clearly. But your physical hardware is only the first filter. The signal that reaches the brain is rarely perfect or complete. Think about trying to understand someone talking in a crowded restaurant. You don't hear every single syllable, yet your brain constructs a coherent sentence. It's performing something called auditory scene analysis, separating the meaningful signal from the noise and filling in the gaps. The Yanny/Laurel clip is auditory noise. It's an ambiguous signal with two plausible interpretations. This filling in is not a conscious choice. It's a fundamental process. Your brain abhors a vacuum. Much like how it invents information to cover the physiological blind spot in your retina, allowing you to perceive a complete visual field, your auditory cortex constructs a definitive word from an indefinite sound. It receives the messy, overlapping frequencies of the clip and collapses them into a single, stable perception. It has to choose one. How does it choose? This is where top-down processing takes over. Your brain uses context and expectation to guide its interpretation. This is the priming effect. If you see the word Yanny written down before you listen, your brain is primed to search for acoustic patterns that match it. It actively directs its attention to the high-frequency data, effectively ignoring the lower-frequency information that suggests Laurel. Your expectation becomes a self-fulfilling prophecy. This isn't just a party trick. It's how we understand speech every day. The sentence, "I have a big nose," and "I have a big nose ring," can be acoustically ambiguous at the end. The context of the conversation, the speaker's identity, your knowledge of the world, all of these prime you to hear one over the other. In a famous experiment, subjects heard a sound that was an ambiguous mix of a cough and a word. If told the study was about illness, they heard a cough. If told it was about language, they heard the word. Beyond priming, there are inherent individual differences in auditory processing. Some people may have a natural attentional bias toward higher frequencies, which are crucial for distinguishing consonants like s, t, and y. Others might focus more on the fundamental frequencies and lower harmonics that give a voice its body and define vowel sounds like o and ah. This isn't about better or worse hearing, but a subtle, subconscious strategy for processing the auditory world. Your brain may simply be a Yanny first or a Laurel first processor. To see the ambiguity, we have to look at the sound itself. A spectrogram is a way to visualize sound, showing frequency over time. In the spectrogram for this clip, we can see bands of high energy called formants. These are the resonant frequencies of the speaker's vocal tract. The specific frequencies and movements of the second and third formants are critical for how we differentiate vowels. Here, they sit in a precarious middle ground. They possess characteristics that could be interpreted as the a and I in Yanny, or the ah and in Laurel. Think of formants as the acoustic signature of a vowel. By slightly shifting the frequency of these energy peaks, you can change an E sound into an U sound without changing the fundamental pitch of the voice. The original recording from vocabulary.com has a peculiar combination of a low fundamental pitch, characteristic of a male voice saying Laurel, but with formant structures that contain enough high-frequency energy to trigger the perception of the word Yanny. The illusion is baked into the physics of the sound wave. This perceptual split is not a bug. It is a feature of an incredibly efficient system. Your brain operates as a prediction machine. It constantly generates models of the world and uses sensory data to update them. When the data is ambiguous, as in this clip, the brain defaults to its prior model, whether that's shaped by age, attention, or recent priming. What you hear is not the sound wave itself, but your brain's best hypothesis about what caused it. This principle extends across all senses. Consider the McGurk effect. When you watch a video of a person's mouth saying ga, but the audio is actually the sound ba, most people will hear da. Your brain receives conflicting data from your eyes and ears and creates a third, entirely new perception that reconciles the two. It trusts the visual information of the mouth shape so much that it alters the auditory signal. Perception is a multi-sensory negotiation, not a direct report. Ultimately, the Yanny or Laurel debate is a profound, accessible demonstration that objective reality and perceived reality are not the same thing. The pressure wave that enters everyone's ear is identical. Yet inside the silent, dark theater of the skull, two different, entirely valid subjective experiences are constructed. It reveals that we don't just passively receive the world, we actively create it, moment by moment, with every beat of our heart and every firing of a neuron. Monotony has grown fast. Nearly 2,700 people have watched in the last few weeks, yet less than 0.03% are subscribed. It would mean a lot if you joined by hitting subscribe. And again, thanks for watching.